Imagine a huge asteroid crashing into the Earth. Not some kind of pebble only 5 miles in diameter that killed dinosaurs, but a 100-mile comet. And does it in such a way that we are not aware of it. Is this possible? Actually, why not? What exactly is hard for you to believe in? That objects of this size exist? Well, there are tons of them. That such an object could collide with the Earth? Well, easily. There's only one thing that is hard to believe in, that such a disaster could have happened quite recently, and even somehow managed to remain unnoticed. Really? But all researchers of alternative history claim that something fell on us in the 17th century, right? Then why does such a simple calculation of their own theories cause rejection? The official science is not witty in this matter. Have you ever heard what the officials say about the origin of clay? Historians and biologists are sure, for some reason, that clay is fermented horse feces and other organic matter. But do you know the composition of clay? It includes aluminum, silicon, and oxygen, with other solids. I will believe the official version if they show me a horse shitting with aluminum oxide and quartz. But we'll get to it later. So, let's start from the beginning. Could the planet survive a collision with such a monster? Could people survive it? Some dawning on civilization? We know that the Apophis asteroid with a diameter of only 650 feet, which constantly frightens us, can destroy us all. That's what we are told from the TV. We have seen so many movies about the end of the world, how the planet is torn apart, how it is covered with lava and the core splashes out. We are told a lot of things, for example, about Iron Man, Batman, Spider-Man, and Terminator. But these are all illusions, fantasies, an odd property of human psychology which allows us to shout that everyone is lying to us, that no one flies into space, and then assert that, according to scientists, a meteorite of 5 miles in size is enough to destroy life. What if this is also an illusion? What's the truth? Let's find out. First, let's study the real consequences of the collision of meteorites with the Earth. Conveniently, there is a program on the website of the Imperial College of London, which already contains the basic formulas to let you calculate the effect of the collision of the Earth with various celestial bodies. I suspect that all those shouting about the impossibility of survival used the same program and the same formulas. Well, let's try to use it too. Here you can set some parameters manually. For example, the distance from the observer to the impact, the diameter of the body, its density, the speed of impact, the angle of impact, as well as the density of the surface at the collision site. Well, for example, it could be water or rock or ice. To begin with, let's see what happens if an object with a diameter of 50 miles hits the Earth. We got this diameter in the first part. Let's set its characteristics according to the classical idea of meteorites. That is, let's make it iron. We'll set the standard cometary speed of 31 miles per second with an impact angle of 48 degrees. And let it hit a rock, for example in the Himalayas. At this moment we are sitting, for example in Moscow, at a distance of 2,330 miles. The results are impressive. The crater is 990 miles. Half of the Earth will be demolished by a fireball at a distance of 1,050 miles. But in general, no one will like it. A third of all living beings on Earth will be demolished at once. But notice that the Earth's axis will not move a single degree, and humanity will still survive. Although, maybe not for long, for a month and a half or two. Now, let's do the same thing, but this time with a comet. So the cometary body is much less dense. As a result, the crater is much smaller. Although it's still 450 miles in diameter and it shakes the Earth much less, the consequences are still very severe. But the Earth's axis didn't move again. Now imagine the impact of a 125-mile body. The results are quite bad. A crater 2 miles deep, 860 miles in diameter. All buildings on Earth were destroyed. Volcanic activity began. An earthquake of 13.3 magnitude on the Richter scale. What can I say? This dummy almost split the planet like a bullet splits a watermelon. Even the orbit has shifted, but the axis, by the way, didn't move again, even by 5/100ths of a degree. Maybe we set the angle of incidence or speed incorrectly. No, angles of any degree don't affect the situation much. Neither do any speeds. Finally, let's enter the collision of the Earth with exactly the same planet into the calculation parameters. Of course, everyone died, but the axis almost didn't move again. So, it turns out that no forces can move the Earth's axis, not to mention a comet or an asteroid. Maybe scientists are lying. Maybe they use some incomprehensible miracle formulas in the program. Keep this result in mind. We will definitely return to it in the future, and it will allow us to make a shocking discovery. And now, let's try to answer another question. Is it possible to notice such an enormous blow to the planet? A collision with such a huge object? As it turns out, it's possible. The thing is that mainly iron meteorites fall to Earth, and they make an impressive punch, and their entrance is spectacular. While comets don't fall at all, even though they scare us. And we're missing a very important detail here. Here we have megatons of sand and clay before our eyes, but we analyze it like an iron meteorite. Even though iron is far from the most common element in our solar system, even in the galaxy, iron and other elements heavier than iron appear only at the moment of a supernova explosion. Actually, it's a kind of detonating fuse for stars. As soon as iron begins to be synthesized in the core of a star, this means that the star will explode very soon. The most common elements in space are, of course, hydrogen and helium. Carbon and nitrogen are in third place, followed by oxygen, neon, sodium, manganese, aluminum, and silicon. Iron is only 16th in this list. And what do our deserts and clay rubble consist of? Deserts consist of silicon in various combinations, including with aluminum. And clays also consist of silicon oxide, aluminum oxide, and water, as well as carbon in various combinations. These are the elements that occupy the 1st, 3rd, 5th, 9th, and 10th places in terms of prevalence in the solar system and the universe in general. And if we consider metals, aluminum is the most common metal in the universe. It is logical to assume that the terrorist asteroid we're looking for should consist of such a set. Of course, there will be iron too, but in scanty quantities. So, let's take a look at our solar system and see if there are objects suitable for the description anywhere else. It turns out that there are. And there are many such objects in our solar system. They even have their own class allocated for them. These are the so-called asteroids of the Centaur category. There are more than 44,000 of them in our solar system alone. They have a very large range of sizes, from 1 to 250 miles in diameter. The vast majority of them are located far away from us, in the asteroid belt, between Jupiter and Saturn, near Uranus, in the Kuiper belt, in the Oort cloud. Many of them are moons of Jupiter, Saturn, and Uranus. Let's take a look at some of them, the ones that fit most closely into our model. For example, here's one, a satellite of Saturn, Phoebe. And here's another one, Charon. It wanders between Saturn and Uranus like a drunk. And here's Nix. It's hanging around Pluto. What can I say? Even Phobos and Deimos, the satellites of Mars, are essentially the same asteroids of the Centauri category. And there are a lot of them. Look them up sometime. So, what do we know about them besides their orbits and masses? We know that some of them contain unusual compounds in small quantities: tholins, amorphous carbon, soot, olivine, and water vapor. But this is in small quantities. And what about large quantities? We also know their density. Well, not everyone's, of course, but some of them. For example, the Charon's density is about 2 grams per cubic centimeter, and the density of Phoebus is 1.6 grams per cubic centimeter. It would seem, well, what's the big deal? Well, first of all, it means that they are not made of gas or even pure water, which has a density of 1. So, they're not comets. But they're not made of iron either. It has a density of 8 grams per cubic centimeter. The difference is huge. But any man who has built something with his own hands at least once in his life will see that Charon consists of something similar to a mixture. For example, clay. Its density is just in the ranges from 1.8 to 2 grams per cubic centimeter. And Phoebe is basically pure sand, which has a density of 1.6. Well, congratulations. You have just completed a course of a young astronomer. Go ahead, discover new sand and clay asteroids. And we've just found what we were looking for. There are such bodies in the solar system. They don't just exist. There are many of them. And if so, then the probability of a collision of the Earth with such an object always exists. In no case should it be discarded. This is the main idea of this video. But we didn't find the answer to the main and burning question. If that really fell on us, then why did we rather easily survive the fall of such a giant? Why didn't the Earth explode to hell? After all, even if we input an object with a density of water that is less than the density of silicon or clay into the mathematical formula of a collision, the impact is still very strong. Let's try to figure it out in the next video.